Have you ever wondered how your computer can be streaming music, downloading a huge file, and letting you browse the web all at the exact same time? It feels like magic, right? Well, in this explainer, we're going to pull back the curtain on that magic trick and show you how to give your own Java applications that exact same superpower. And trust me, this is a must-have skill for any modern developer. So that brings us to the big question we're going to answer today. How do you actually make a single program do multiple things at once? Getting this right is the difference between an app that feels slow and clunky and one that feels responsive, fast, and, well, powerful. To get there, we're going to go on a little journey, step by step. First, we'll look at the problem, the normal, one-thing-at-a-time world of sequential execution. Then we'll try our first fix, which is going to lead us right into a really common mistake. After that, we'll uncover the golden rule of Java threading, the huge difference between start and run. Then comes the fun part. We'll find undeniable proof that our code is actually working in parallel. And finally, we'll meet the mastermind behind it all, the thread scheduler. Okay, let's dive right in. Before we can really appreciate running things in parallel, we need to get a handle on how most programs work by default. Think of it like a to-do list. You have to finish task number 1 completely, cross it off, before you can even think about starting task number 2. That's sequential execution. Let's look at a super simple example to see this in action. We've got 2 classes here. The first one's only job in life is to print the word hi 10 times. The second one, almost identical, but it prints hello 10 times. Then, in our main program, we just tell the first one to do its thing, and then we tell the second one. Simple enough, right? So what actually happens when we run this? Well, the main method kicks off and calls our print hi method. Now, here's the really important part. The main method is now just stuck. It's totally blocked. Imagine it's on the phone. It can't do anything else until that call is over. It just has to wait and wait for all 10 highs to print. Only after that first task is 100% done can it finally move on and call print hello. And yep, here's the result. The output is exactly what you'd expect from that one-track mind. You get a solid block of 10 highs, followed by a solid block of 10 hellos. It's predictable, sure, and it works, but it's not what we're after. The goal is to see these highs and hellos all mixed up, happening at the same time. So, how do we break out of this sequential trap? Well, our first logical attempt is to use one of Java's core tools for this exact problem, the thread class. Let's see what happens when we try to turn our normal little classes into actual threads. Now, what's really interesting here is just how simple this change looks. All we have to do is add these 2 little words, extends thread. That's it. With just that one change, our boring old objects are now packed with all the capabilities of a thread. They're not ordinary anymore. So that's it. Problem solved, right? We made them threads, so they should just run in parallel. Let's run the code and check the output. And, that's weird. It's exactly the same as before. All the highs, then all the hellos. So what did we miss? This, right here, is a classic trap for new Java programmers. But don't worry, the solution is way simpler than you think. It turns out there is one fundamental rule you absolutely have to know to unlock real parallelism in Java. And it all comes down to understanding the critical difference between 2 methods that look almost the same. Start and run. And this slide lays it out perfectly. On the left, we've got mythread.run. Now, this is what we were basically doing before. Calling run directly just executes the code inside the current thread, just like any other normal method call. No magic there. But on the right, mythread.start, that is the magic button we've been looking for. So what is the actual difference? Think of it this way. The run method is like the recipe. It's the list of instructions for the job you want to get done. But the start method, that's like the manager who hires a brand new worker, hands them the recipe and says, go do this job on your own time. I've got other things to do. Start method is what actually creates that new separate worker, that new thread, and then tells it to follow the instructions in its run method. So here it is, the big takeaway. If you remember only one thing from this whole explainer, make it this. To start a new thread, you must always call the start method. Never, ever, ever call run directly if you want things to happen in parallel. That's the golden rule. Okay, so we know the rule now. We've updated our code, we're calling start. Now it's time for the payoff. Let's go find the proof and make all that invisible parallel processing finally visible. All right, so we run our new improved correct code, and wait a second. the output still looks sequential. What on earth is going on? Did I lie to you? No. The problem here isn't our code, it's our computer. Modern processors are just so ridiculously fast that the entire job of printing high 10 times is over in a flash. The first thread finishes its whole task before the operating system even has a chance to think about switching over to the second one. So, how do we actually see this parallelism at work? Well, the solution is actually pretty simple. We just need to give our threads more work to do. We have to make the job long enough that the operating system has a real reason and enough time to step in and say, okay, thread 1, you've had your turn on the CPU, let's give thread 2 a chance now. And the change to do this is incredibly easy. Instead of looping just 10 times, we're just going to bump it up to 100. That's it. We're just making the job 10 times bigger to slow it down a bit. And now, check that out. Look at that beautiful, glorious, jumbled output. This is our aha moment. It's all mixed up. We get a hi, then a hello, a couple more highs, some hellos. This beautiful mess is the undeniable proof that our two threads are running at the same time, weaving in and out as they fight for the processor's attention. We did it. So who or what is actually managing all this elegant chaos? It's time to meet the real mastermind working behind the scenes, the thread scheduler. This is a core part of your operating system, and it's responsible for juggling every single thing your computer is doing right now, from updating the clock to playing this very explainer. Now, this slide really puts the challenge into perspective. On my machine right now, there are over 2,300 threads, just waiting for their turn to run. But I only have 8 CPU cores to do all that work. How is that even possible? How can you run thousands of tasks with only 8 workers? Well, this is where the scheduler's genius really shines. It's like a grandmaster chess player playing against thousands of opponents at once. They make one quick move on one board, then instantly jump to the next, then the next, and the next. The scheduler gives each thread a tiny fraction of a second, a time slice, on one of those CPU cores. And by switching between all those threads so incredibly fast, it creates the perfect illusion that everything is happening at the exact same time. So, let's do a quick recap. You now know how to take a normal sequential program, turn parts of it into threads, and use the all-important start method to set them running in parallel. You've seen the proof with your own eyes, and you've met the thread scheduler that makes it all possible. But creating threads, that's just the first step. The real challenge and the topic for our next explainer is this. What happens when these threads need to share data or talk to each other? That, my friends, is when we enter the truly wild and fascinating world of concurrent programming.